This again. Gravitational potential energy and its consequences. Here we go. So let's do a little bit of review first. Who remembers, and hopefully you all do, the equation that allows us to calculate the gravitational force between two masses? I'll go with that, right? You guys remember that one? Okay. Newton's law of universal gravitation, right? G/m over r squared. Everybody good with that? Comfortable? Seen that before at least? How about this question? This one's a little bit trickier. What is the gravitational field? We represent it with the letter little g. And how is it represented? How do we describe it? So what is the gravitational field? So good. So the definition of gravitational field strength is the force, the gravitational force that a mass feels at a location per unit mass felt by a small mass. That's its definition. It is 9.8 here on the surface of the Earth. And there's equations for it, right? So here we go. The gravitational force per unit mass at a specific location. That's the field strength. The equation in your data booklet is this one, G equals F over m. So field strength is the force per unit mass. There's your definition right there. Felt at a location in space, felt by a small mass. This second equation is not in your data booklet, but if you combine this, since that equals force, you plug it in over here for force, you will get this equation, right? G/m over r squared over m gives you Gm over r squared. The main thing for you to remember about these two equations about gravitational field strength is this first one is describing the field that a mass is experiencing, and this one is describing the field that is generated or created by a mass. So the second one is usually like calculate the strength of the field created by Jupiter or by the Earth or by some huge mass. This one is saying, oh, you're standing there in space and you feel this much force. What's the field strength there? Okay?
So big M is what's like causing it.
And then finally, Shayla, just like you'd mentioned, the field strength at a location is exactly the same value as the acceleration caused by gravity at that location. So if you drop something and you measure its acceleration, you know the strength of the field. Or there was an interesting question, I think, on the test where you have an orbiting satellite, and if you can calculate its centripetal acceleration, and that acceleration was caused by gravity, that must be the strength of the field. Okay? All right, so that's just review. Okay, we're still reviewing now. We've talked about potential energy. Who remembers what potential energy is?
So the potential energy concept.
How have we talked about calculating potential energy? It's not real complicated. It's 3 letters. MGH, mass times the gravitational field strength times how far you've moved it through that field. That's what H stands for. Okay, so that's how we calculate potential energy when distances are small. This is a great equation if I'm lifting something a couple of meters or a couple of 100 meters. That works great. But as soon as I use, like, let's say a rocket, and I lift something from the surface of the Earth to the moon or the surface of the Earth to Mars, this equation is useless. Why is it useless? That's a good. Okay, what happens? Does G stay constant from here to the moon? No. Okay, so G doesn't stay the same. What about H? What do we measure H relative to? Okay. So since G is always changing on large distances, and H is hard to measure when we go really big distances, we need some sort of universal measuring point. To figure out, if we want to measure the potential energy of everything in the universe, we need to have a frame of reference to measure that energy from. And what do you think people have chosen to be the ultimate reference frame for potential energy? Infinity is what we've chosen. Remember that? Remember that? Okay. So the ultimate reference point for potential energy is actually infinity. If we want to measure the potential energy of everything in the universe, we're going to say, how much energy does it have, or how much work does it take to move it from infinity to that location? And then we'll know what its potential energy is. Okay? And since G gets smaller and smaller, since little g, the gravitational field gets weaker and weaker the farther, let's just imagine Earth right now. Forget about all the other stars and galaxies. If I lift something from Earth, G gets smaller and smaller and smaller, okay? The field gets weaker. And if I took something all the way to infinity, the field would be 0. There would be no more pull. The Earth would no longer be pulling on it gravitationally. So what we would say is it would have no potential energy there. So by definition, at infinity, potential energy is 0, which means that potential energy is actually negative here on Earth. You start with negative, and as you lift something up, it increases its potential energy all the way until it reaches 0.
So it just keeps going up and then it just drops?
No. So if I can figure out how much work is done in moving an object from infinity to wherever it's located in the universe, then I can tell you how much potential energy it has. That's kind of our new reference frame, right? But in order to do that, we'd have to do some calculus. So we're not going to, but let's just kind of walk through it real quickly anyway. What? Oops, I'm not going anywhere. Okay. We know that work equals force times distance. Okay. And force, when we're talking about gravitational potential, the force is gravity, gmm over r squared, times distance. But now I'm going to use r and d. I'm going to make those become infinity to wherever we're located. And when I do that with calculus, it's fine. If I do it just with algebra, it gives you weird answers. And what we'll find out ultimately is that the potential energy that an object has at any place in the universe now is equal to negative g mm over r. M being the mass of the object, the other m being the mass of the thing that's creating the gravitational field. In this case, we could think of it like the Earth or the Sun or something like that. Okay.
Wait, can you explain?
So this final equation now, really what I've been trying to get at just with this whole page of notes, is that this equation is now much more universal than this equation. This equation works for really small distances. This bottom equation works for anything in the universe, anywhere in the universe. Okay? So graphically, what this would look like is that. Okay? It's supposed to be smoother. That's because I drew it by hand and I did a bad job. But this is supposed to be smoother. But notice that as something moves away from an object, okay, this is the distance away from an object, okay, its potential energy increases. It's just like lifting something up. You gain potential energy. And it increases to 0 at infinity. All right? That's what kind of we're talking about earlier. And notice that the rate that it increases decreases, if that makes sense. The rate of change diminishes. So the greatest increase in energy happens immediately. And then as you get farther and farther away, for every meter that you lift it, it gains less and less energy. And that's because the gravitational pull is getting weaker and weaker and weaker.
Wait, isn't that what we've been talking about?
Now we're going to try to get this concept out. Notice there's one word missing. We've been talking about potential energy. Now we're going to just talk about potential. Okay? They are very closely related, but there's a slight difference. Recognize that gravitational potential is represented by the letter capital V. Capital V, we call that potential, because it also stands for voltage, which is electrical potential. Okay, and you've heard voltage before, right? Now, this is a capital V. Velocity is lowercase v. So that's one thing to keep those straight. Lowercase v is velocity. Voltage is electrical potential. So remember we said that the gravitational field is the force per unit mass? You guys remember that? Okay. Well, this has to do with energy. We call it potential, and it has to do with energy. And if you think about potential energy, can you guys see the red on the blue okay? Is mgh. Well, notice that the potential energy that something has is determined by two things, even though there's 3 variables here. It's determined by the mass of the object and then where it's located. Where it's located in a gravitational field. This idea of where it's located in a gravitational field, of this property of the space in which the object is located, giving it energy, this is known as potential. Okay? So if I know the potential at a location, I can tell you how much energy something will have if I put it there. Okay? So let's backtrack from that just a little bit. And so, Tiger, I think you hit it right on the head. I think it was you that said that. The potential is the amount of energy per unit mass at a given location. Okay? Okay? So gravitational field is the amount of force per unit mass location. Potential is the amount of potential energy per unit mass at a location. Okay? So it's a property of the space around it, and it tells you kind of how much energy is available in that space. All right? Let's see. If you can figure out how much work is done per unit mass to move an object from infinity to that location, that'll tell you the potential at that location. Remember, work is energy. So if the work done is equal to the potential energy, divide that by how much mass it was, moving an object from infinity to that location, and I'll know the potential at that location. So mathematically, it looks kind of like this. By the way, it's a scalar quantity. Direction is not really important with potential. It's the work per unit mass or the energy per unit mass that an object has at a location. And mathematically, how would we calculate it? Well, here's the equation for it, and that equation is in your data booklet. V equals negative g times the mass over r. Now, in this case, this is the mass creating the potential. Remember, it was gm over r squared for the mass creating the gravitational field. This is allowing us to calculate the gravitational potential at a location. Okay, so let's see if we can get a little concept of what's going on here. So here's a picture. Imagine this is Earth. 0 meters is the bottom here. This would be like on the ground. And I got 1, 2, 3, 4 meters. The green lines would represent the gravitational field that we live in right now. And it acts downward with a strength of 9.8 newtons per meter. And if I drop something, it'll accelerate along those field lines to the ground. Okay? If I have a mass, let's say I have a mass right here of 2 kilograms, and let's say I lifted it through the field up to here, how much potential energy would it have? 8. This is on Earth. 8. Yeah, so 8 what? What do we measure energy in? 8 joules. This thing just gained 8 joules of energy. You with me? Everything good so far? I think, is that right? MGH? Oh, wait. So 80. 80 joules. That's better, right? Mass times 10 times 4. 9.8 times 4. Okay? Great. If I had a mass of 3 kilograms and I did the same thing, how much energy would it gain? 120, is that right? You guys are fast. Okay? 120 joules. So these two objects have a different amount of potential energy at this location, but it just turns out that the potential is the same. Because this is 80 joules for 2 kilograms, right? And this is 120 joules for 3 kilograms. So how many joules per kilogram? 40. So the potential at this location, we're going to go with a different color. The potential V is 40 joules per kilogram at this location in space. Make sense? That's only for that particular space. But notice that I can actually connect these all along. Now notice I lifted these objects through a field. If I moved it from here to here, along that line of potential, would the energy change? No way. And we call that line a line of equal potential or equipotential. It's an equipotential line. Okay? The last thing I want you to notice about this diagram is I just drew a line of the potential being 40. I could draw another line right here where the potential is 20, okay, joules per kilogram. Notice that my lines of equal potential are always going to be perpendicular to my lines of gravitational field. They will be perpendicular to one another when you draw these things. So you get field lines going one way, you get lines of equal potential going another way. And this is kind of a simple situation because the gravitational field was nice and uniform. So here the green lines are the gravitational field around this planet. Think about field lines. The closer together they are, the stronger the field is. So notice these lines get closer together as you are closer to the planet. That's because the field is stronger. If I was to draw lines of equal potential around this planet, it would look like this. Circles. And there'd be two things you have to recognize. Notice my lines of equal potential are always perpendicular to my field lines. And the farther away I get from my planet, the farther away the equal potential lines should get. Okay, so actually if I was to draw another one, it'd have to be real close in. Because the field gets weaker the farther away I get, then the potential gets farther and farther apart as well, which goes back to that graph we drew before, how my potential energy started to become asymptotic to 0 the farther away I got. Something to consider, and Ivy likes to ask questions about this, is that the change in potential from one location to another does not depend on the route you take. Okay? So if, for example, if I say this is at 0 potential, and this location up here is at 10 joules per kilogram, and if I go from here to here with a 1 kilogram object, it gains 10 joules of energy, right? Yeah? But if I go from here to here to here to here to here, it still gains 10 joules of potential energy. And if I go from here over here to there and around to the counter store and back to there, it still gains 10 joules of potential energy.
What matters is the ending point?
IB question for you to start thinking, talk to your friends, talk to your family, see if you can figure this one out without a calculator.
Wait, if you go back
So-
to the slide, you gave us false information.
All right, so here in the classroom, this was a challenging one, but we finally came up with the fact that A is the correct answer. Because this is not an actual thing, but this is a thing. Okay? Here is an excellent summary of everything gravitational. An excellent summary of everything gravitational. So let's work through it slowly. You can take a picture of it with your iPhone if you want. Let's start with this first line. When we're talking about gravitational force, we can do it two ways. mg, right? That's the weight of an object. That's easy. If I know the gravitational field strength, I just do mass times the field strength. That tells me how much gravitational force it feels. Or I use the law of universal gravitation between any two objects, gmm over r squared. And the units for force are newtons. Okay? If I want to talk about gravitational field strength, this is our basic definition. It's the force per unit mass. But if I want to measure the field strength anywhere in the universe created by an object, I don't have that there, but I can combine these two things. This, though, is what we were talking about with that graph earlier. If I have a graph of potential versus displacement or distance, then the slope of that line will be the field strength, and the units will be newtons per kilogram. Potential energy on a small scale can be calculated by mgh, and on a more universal scale can be calculated negative gmm over r. Okay? That allows me to calculate the potential energy of an object anywhere in the universe. This equation is not in your data booklet. I don't think you should memorize it or write it on your leg or anything else like that, because if you need to use it, I'm assuming it will be given to you because IB doesn't expect you to memorize a bunch of equations. But know that there's a more universal way of doing it, and it's just the way we calculate it was the work per unit mass by moving a distance from infinity to that location. Finally, guys, this topic we talked about today, the idea of gravitational potential. It's equal to the amount of energy per unit mass that something has at a given location, that a small mass has at a given location. And it can be calculated anywhere in the universe by negative gm over r. A certain distance away from a big mass like a planet, I can calculate the potential at that location using that equation. And its units are joules per kilogram. Very similar to field strength, which is newtons per kilogram. But this is force per mass. This is energy per mass. It's the only difference. So this is in your data booklet. This is a piece of your data booklet, the equations that you have. So let's just look at real quickly what we've gone over so far. Yes, right? Gravitational force? No, don't worry about it yet. We haven't talked about it yet. Gravitational field strength? Electrical field strength. Haven't talked about it yet. Okay? Electrical force, electrical force. Don't worry about that yet. Okay? Over here, potential, energy per unit mass. This is electrical potential. We haven't talked about it yet. Okay? Potential, negative gm over r. This is electrical potential. We haven't talked about it yet. Gravitational field strength, electrical field strength. All right? So in your data booklet, as you're preparing for the exam, those are the ones you want to work with, and don't worry about the ones on the right because we haven't talked about them yet. Let's talk briefly about this concept of escape velocity, which I think you guys have already messed with a little bit on some of your homework. Okay? Remember that potential energy is negative here at the surface of a planet, and it increases to infinity, increases to zero as you go to infinity, right? So you can imagine that you live in the bottom of a well of energy. Okay, what's called a potential well sometimes. And like, can you guys see that green on the blue at all? So here you are down at the bottom of a well here on the surface of the Earth. If you jump up in the air, you give yourself some kinetic energy, and your potential energy decreases, and then you come back down. Hold on a sec. If you jump even faster, you give yourself kinetic energy, and then you come back down. But there is a speed at which you could jump so fast that you would have so much kinetic energy that you would have more kinetic energy than this negative potential energy that exists in this well, and you would actually leave the well and never come back. Just go to infinity. And the speed with which you would take to do that is called the escape velocity, okay? So what we need to figure out is how much kinetic energy does it take to overcome the amount of negative potential energy you have right here in this gravity well. Does that make sense? So here's this potential well that we live in the bottom of, negative GM over R. But we have this kind of negative potential energy, GMM over R, right? And if we get more kinetic energy than that, we escape the gravity well and we leave forever. So basically, here's how we could set it up. We could say, ooh, 1/2 mv squared, that much potential energy. If I set that equal to that much kinetic energy, if I set it equal to how much potential energy I have right now, then I can solve for V and figure out the escape velocity from this object at this distance from its center. So by rearranging this equality, I get this for escape velocity. Escape velocity is equal to the square root of 2gm over r. So I think you got a lot of you guys who were trying to memorize that equation for the last test and stuff. It's not in your data booklet, but this is where it comes from. Kinetic energy being equal to the potential energy that you have right here. It turns out here on Earth, it's about 25,000 miles an hour, which if you launch something, if you threw something at that speed so it would leave Earth and never come back, it would fry in the atmosphere because of the friction and the air resistance. It would be horrible. All right. Something to consider about escape velocity. With this equation, as the mass of the object that you're leaving gets larger, what happens to escape velocity? Gets larger. And as the radius of the object that you're leaving gets smaller, what happens to escape velocity? It also gets larger. Both of those things will make the escape velocity larger. More mass, less radius. So you could imagine that as something gets bigger, more and more massive, and smaller and smaller and smaller, it gets harder and harder to leave, and the escape velocity gets greater and greater and greater. And you could theorize that there would be an object where the mass was so big and the radius was so small that the escape velocity would be greater than the speed of light. And we'd call it a black hole. And that's what a black hole is. It's something that is so big, massive in terms, and so small in size that its escape velocity is greater than the speed of light. You'd have to go faster than the speed of light to leave its gravity well, and light doesn't leave it, nothing leaves it. Okay? IB question. Try it out. See what you can do. See what you can do with this IB question. Okay? Super simple. We were just talking about it, so the answer is yes, A, both the radius and the mass of the planet. Okay. Finally, let's talk about satellites. Satellites, because if you think about satellites orbiting the Earth or orbiting anything, and gravity is what's keeping it in orbit, so there's gravitational force acting on it. Let's talk about satellites in terms of energy. Will a satellite have kinetic energy?
Yes.
And will it have potential energy?
Yes.
Yes, of course. It has both. Great. And the potential energy is equal to negative GMM over R. The kinetic energy is 1/2 mv squared, and it has both. So this third line is just showing you that the kinetic energy that a satellite has is always going to be half of its potential energy. Okay? The total energy is the sum of its kinetic and potential energies. And don't worry about the math of that so much. So the kinetic is always half the potential, and the total energy is always negative. So let me show you what a graph of all this looks like. Here's what I'm talking about graphically. Okay? A satellite, which is basically anything that's orbiting something else gravitationally, as you move, let's imagine right now this is just satellites around the Earth. As I move away from the surface of the Earth, the potential energy of that satellite increases. That makes sense, right? And the kinetic energy will decrease. A satellite at a higher orbit moves more slowly to stay in orbit. And the total energy is always going to be the sum of those two. And this kinetic energy at any location will be half the potential energy. So if the potential energy here is -8, then the kinetic energy is 4. And the total energy is -4 at that location. Okay?
Wait, so it can never be positive? What? We're all set on that.
Final question. Final question. So what's the correct answer, you guys? A is the correct answer.